Desmos is still working. Yeah, I've still got Desmos. So even if yours is not working, I'll graph it up here so we can see. I also numbered these problems wrong. That should have been a 2 right there. Let me fix that right now. All right, so I think these are kind of cool problems here. Um, Definitely not something you would do like on a daily basis, but if you were somebody like designing things, then you would need to think about this stuff. So I don't know if you guys have ever done this, but I can remember doing things like this whenever I was a kid. Like I would um, always like really crafty things. Anyway, um, so if you take, where'd my scissors go? Um, if you take a sheet of paper, so like right here, we've got an 8.5 by 11 piece of paper, like the problem says, right? If I take my scissors and I cut a square out of the corner right here, and then I cut that same size square out of the corners over here, so all 4 corners get cut out here. Like this. And those are probably not perfect squares, so this won't be perfect. But if you cut all the corners out, then you can fold it on the little flaps, and you will have you a nice little box right there. My squares weren't perfectly square, so I got one side a little higher than the others there. But you could make a box out of this, right? So, like if you are, uh, like in a shipping company or whatever, um, you're gonna have all kinds of boxes, all kinds of different sizes and things, and probably not like the actual shipping, like your UPS. I guess you would be box manufacturers. I don't really know, but like you would have a lot of different size boxes and different things that you would need. And this is still more or less what happens with it, right? Like you are doing something of the sort. They'll have different ways that they like brace it or make it like sturdier there. But all your boxes come from like flat sheets of cardboard to start with, right? The question that we have here is we have an 8.5 by 11 piece of paper. We're going to cut squares out of the corner to form an open box like shown. What is the maximum volume that you can have of the box? So, my box right here is sort of short and flat, right? Would it be better to have maybe a taller box or a even more shallow box? What would give us the biggest volume? Because as we change the sides here, we would get different volumes. And if you are shipping something, you would probably like for your box to hold the most stuff, right? So we can do this by setting up an equation. What we need to do is we need to think about what this is going to look like once it is constructed, right? So like whenever we take like these, you'll cut this part out here, and then like what I'm drawing in right here, this would be where you would fold the flaps, right? And this part right here would be the bottom of your box. So you would end up with a box that looks this, okay? And so the bottom of the box would be this part here, and then you'd have these little flaps that get pulled up on the sides, right? So if we're taking out a square here, then I could call, in fact, let me not make that an X. I'm going to just like do this to make it go away, because that might get confusing with what I'm about to do. This little piece right here and this little piece right here, they should be the same length, right? And I don't know what that length is, so I'm going to call that length X, because X is our favorite one to use. Okay? So, if you think about folding that up, whenever you have that like length right here that is X, when you make your box and you fold it up, which piece of your volume is that going to be? Is that going to be length or width, or is it going to be the height of the box whenever you fold it up like that? Height. So that means that like the side of the box right here, the height of that box is going to be X. Now what's trickier is finding the length and the width. Okay, now this piece of paper was 11 inches this way, and it was 8.5 inches this way. Okay, but I don't need that length all the way across. That's not, like, the length all the way across is not the bottom of my box, right? So what I've got to do is think about what's happening here, and I've got 11 inches right here, and I took away this length right here and this length right here. So what could I use? What could I call that side right there? We won't have like a number answer. I could use a different variable, but I don't want to do that because that would like make it harder to figure anything out there. So using what I know here, this whole side was 11. What did I take away? Whenever I cut this piece out and this piece out, what did we call the lengths of these? They're X's, right? So I could call this piece 11 minus 2x, right? I took an x out of either side. So this piece right here could be 11 minus 2x. Okay, so let's think same thing right here. What about this piece right here? What could I call that piece? 8.5, and then what, Zoe? Minus 2x, because this whole side right here was 8.5, and I took an x out of this side and an x out of this side, so I subtracted 2x. So this piece right here is 8.5 minus 2x. All right. So I can write a volume equation for this, right? Volume of a is it good? Don't go back to the quiz right now, though. I do not want you finishing the quiz right now because I need you paying attention to this. All right, so volume could be x times 11 minus 2x times 8.5 minus 2x. That is our volume formula. Now from here, we're going to use Desmos. We're not going to try to do any of this by hand. So what I'm going to do is go over to Desmos, and if your Desmos is working, you can use that as well. But I'm going to say V of x equals x times 11 minus 2x times 8.5 minus 2x. And it's going to give me this weird graph here. what is the question asking me to find? Maximum volume. So I have a maximum. I also have a minimum. But what we're going to see is like the equation stops making sense at a certain point. Can I have a negative volume? Is that possible? No. So like really right here, that's as far as you can go. The equation stops making sense after a certain point. What we want to see is this piece. Oh, sorry. What we want to see is that point where it got to its highest point. Yes, it goes higher over here, but this is like we've already gone to negative volumes here. The equation doesn't make sense after this point. So if I click right here, I get 1.58542 and 66.14823. What does our x coordinate stand for? What does our y coordinate stand for here? Not radius, because that'd have to be for like a cylinder, but it's going to be a length. The y is definitely volume, right? The x is just the length of that square that we took out of the side, right? So to get the biggest volume for this particular scenario, you would want to take out a square that was like about 1.6 out of each side. It would give you a volume of 66.148 cubic inches. And this question asked for the maximum volume, so we want to get volume. It didn't ask for the length of the square for that. So if I took out a square, you know, this equation gives us like, if you took out a square that was just like 1, oh, it's going to be hard to get to that. Like, if you took out a square that was just like half an inch, your volume would be only 38. If you took out a bigger square, like a square with 3.28, then your volume's only 28, right? It gives you the volume for any decision that you might make there. Okay, questions? All right, let's do a similar problem. You need to know how to do these problems, okay? All right, so first thing I'm going to do here is I've got this particular case, and they give us the length of the sides here. So I need to figure everything out. So if they cut 4 inches off here and here to make this box, I need to sort of label the different pieces that I would have. So like this to this, that'd be this side right here on my box, right? How long would that side be? How long would this blue side be right here? Okay, the whole length of the bottom side is 36. Well, in this particular case, they tell us how big the square is that they cut out. 36 minus 8, because we do 36 minus 4 minus 4, right? And so 36 minus 8 would give us 28 inches here. Okay? Then I need to know, actually let's do the one that I think is maybe the easiest. What is the height of this box? Like if you think of folding that up, it's going to be 4. And then, because that's just a little flap that gets folded up there, right? That would be 4. And then the other piece that we need, let's do that one in green, is going to be this piece right here. That piece is like this part right here. Y'all were just guessing. I think I heard the right answer. 14. How'd you get that, Jose? Okay, where'd you get the 18? Okay, this right here would cut that side right there in half, right? So this part would be 18. This part right here is 4 because it's one of the little flaps that folds up, right? So that leaves us with 14 right here. So this side right here would be 14 inches. Okay, you guys see where that comes from? Okay, now this problem's not a variable problem. This is just asking us to find the volume, right? So the volume for this is very straightforward, 28 times 14 times 4. And if we type that into Desmos there, we got 28 times 14 times 4. We're going to get 1568. And that would be inches cubed there. Okay, questions there? Does that kind of make sense, what we did? All right, so you'll notice the next problem is the same picture, right? What did I change about this scenario? I got to maximize, and do I know how big the corner square here is now? I do not. So this one's going to be one with variables in it, okay? But it's going to be done pretty much the same way as we did on the other problem. So like this side right here is going to be this bottom side. So we did 36 minus 4 last time. But what is the length of the square now? It's x, right? So this piece is going to be 36 minus 2x. What's the height of the box going to be? Right, it was 4 on the last one. It was that little flap that got folded up. So this piece right here, that little flap that gets folded up, is x now, right? Okay, and then I think the hardest one is to do this piece right here, which should be right here. What do you guys think about that? What? It's not going to be 14 this time because I don't know, like this piece right here, last time it was 4. This time I don't know what it is. I just know it's x. 18 minus x. Beautiful. Right there. Because we could still cut this in half right here. This is 18, right? And so we could do 18 minus x. So our volume here, Fernando, what would that volume be? Okay. Oh, sorry about that. I don't know what I did. But we just multiply those 3 things together, right? And so this could be really difficult if they didn't let us use Desmos. But we just want to type that into Desmos. So we're going to have x times 36 minus 2x times 18 minus x here. It's going to give us, sometimes it's hard to see when you zoom out on that. Instead of zooming out, it might be good for us. Like, I know it looks like I'm going to get a pretty big number. Like, might make this like 200. Oh, that's not enough. Let's do like 500. Oh gosh. We're going to get a big answer here, aren't we? Okay, let's do 2,000 then, based on what Fernando said. Okay, that looks better, right? And if you look right here, it's 6 and 1728. But let's read the question. I really didn't even read the question from the beginning. If the grocer from the last problem wants to maximize the volume of the box that he can cut from the 36-inch square of cardboard, what should the height of the box be? Okay, so in this case, they're not asking us for the volume, they're asking us for the height, so that should be 6 inches there. And if they had asked for the maximum volume, that would be the 1728. Okay, so definitely, I mean, like the grocer himself probably is not doing this, right? But like if you are making a product and you're shipping like large quantities of things, this is something you actually like might think about. It's using less cardboard, which is less waste, so it's good for the environment. It also is less cost because you're using less material. So that is a good thing to know. All right, how's the internet looking out there? Is it working? Yes. Okay. All right, let's skip this one. I want to show you a couple density problems, and then we are going to move on to the. Well, I'll let you guys do the quiz. So I'm just going to do a couple of these. One thing that we'll need to be able to find is population density. Okay, this is a measure that like social scientists will look at a lot. Population density, some places have a very high population density, lots of people per square mile. Some have very small population densities, like Elkin would not have a huge population density. We got a lot of land per person. You go out west, it's even less. Go to New York City or somewhere like that, much higher population density. So a zoo has just opened a new gorilla exhibit that has a total of 54,000 square feet. Zoo regulations require that each gorilla have at least 8,500 square feet. How many gorillas can be housed in this exhibit? Okay, what do you think we should do? Okay, good. We're going to divide 54,000 by 8. Where did my 54,000 divided by 8? Oh, I need one more zero right there. Okay, so 6.353, but you can't have part of a gorilla, so you would just have 6 gorillas. Okay, let's look at the next one. There is an island located off the coast of South America that is approximately 4,500 square miles and contains 608,000 inhabitants. According to the previous year's hospital records, 11,275 children were born last year, but 9,850 inhabitants died. The local government of the island believes that they can support a population that is as dense as 135 people per square mile. Given last year's medical records, can the government support the new population? Okay, so especially when you're thinking about like island communities, this is very important because islands have much more limited resources than larger land masses, right? So you have way too many people in one place, your systems start failing, your sewer starts failing, your water systems start failing. People don't have water, people don't have things that they need to live, and that's a very bad situation. So this would be important for you to know here. So the population was 608,000, but what happened to, we had how many people born? Tell me that one. 11 something. 275. All right. Then we had 9,850 to pass away. So we've got 609,425 people, right? So we got 609,425 people. Okay. What is the area of the island? 4,500 square miles, right? So we just have to divide these to get our population density. Alright, so we got 135.427 repeating. Alright, so the answer to this would be no, because it's over 135. And in this case, you were talking about like a measure, so it's okay to have a partial person because it's an average that's describing the situation. So no, this government would need, now it's not way over, but it needs to be making adjustments to things, right? It needs to be thinking about, oh, can we update our sewer systems so that they have more room? Do we have enough housing, right, to think about what's happening here, okay? Let's do one more density problem. This one's like actual density. So like in a science class, you learn about density. The density of water at 30 degrees Celsius is 995.65 kilograms per meter cubed. The figure below has a mass of 540,000 kilograms. Will it float? That should say, will it float in 30 degrees Celsius water? Okay, so if something floats, its density is less than that of water, right? If it sinks, its density is more than that of water, right? So density is your mass divided by your volume. Okay, so I need to know the density of this object right here. They tell me the mass. It's 540,000 kilograms. I don't want you to round till the end of the problem. For volume, don't round it till the end of the problem. So like copy and paste it for that there. So we need to find the volume of this cylinder right here, right? How do we find the volume of a cylinder? Look at your note card. All right, so for this one, that's going to be pi times 5 squared times 8. So if I type that into Desmos, pi times 8 and 5 squared times 8, I'm going to get 628.318 right here. So 628.3. Okay, that's my cubic meters. So then I have to divide here to find the density. And so if I take 540,000 and divide it by, I'm just going to copy and paste this number right here. I get 859.437 kilograms per meter cubed. Will this sink or float? Float. This density is less than the density of the water, so it's going to float. Right. If we had anything above that density, it would sink. All right, we're going to stop there.